As you can see, I'm the first PhD student probably presenting in, giving a talk in this long program and also in particular in this workshop. So I'm going to be getting super intimidated by your questions, and I will be, very scared. So be careful, but not joking. Yeah, you can ask whatever you want. Anyway, so let's start with, does it work? Okay, let's recall a little bit the general setting. So in the classical optimal transport, we typically have measure spaces and the probability measures, and we have in the simplest case, bounded cost function, and the couplings that are joint probability distributions. In the quantum setting, we instead have Hilbert spaces instead of measure spaces. We have the quantum analogs of probability distributions, which are density matrices. So they're just self-adjoint operators that are positive and have trace equal to 1. And instead of a cost function, we'll have Hamiltonian or like a self-adjoint operator on the tensor product of the Hilbert spaces. And as the quantum couplings, we're talking about the operators on the tensor product, which have correct partial traces. So the problem that was considered in the first talk was the infimum of trace of h gamma, where here the trace is the replacement for the integral is we have in the classical sense. So what we like doing in general for even doing some numerical algorithms, we want to find some regularization. And like this is the problem that Lorenzo was presenting in the previous talk. So as the example of the regularization, you can take the von Neumann entropy multiplied by some parameter epsilon. And so this gives you a little bit of chaos in the system. However, as you send epsilon to 0, you can still recover the solution of the original problem. So what are the advantages of this problem? Is that in this case, because of this entropic term, we have the functional strictly convex, so we have a unique minimizer, and in particular, this minimizer will have the following shape, which is given by the Lagrange multipliers or the actual solutions of the dual problem that we're going to consider after. So there is a big problem, is that it's kind of hard to explicitly compute the iterations to approach our solution. For example, we cannot do a Sinkhorn algorithm like in the classical case. However, we could do some first, second order methods that will still do the job somehow. But okay, we'll see what we can do. So this talk, we are going to be considering, instead of just taking the von Neumann entropy, we're going to be looking at all possible functions phi that are convex and superlinear. And we also considered the unbalanced problem. So this is first time mentioned. So here, this is another relaxation of the primal problem. So not only we have these entropy term with epsilon, we also have the soft penalization on the marginals. So in this case, we consider some relative entropy with respect to the partial traces of your gamma. So in this case, this second problem is defined for all positive semi-definite matrices. And we just want to make sure that this relative entropy is as close to 0 as possible. So in the end, we want to send tau1 and tau2 to infinity, and then we recover the correct marginals. So this is the second problem, sub-problem that we considered in the paper. So in our work, we we decided to stick to one example of the relative entropy, which is Omegaki entropy that was mentioned already many times, I think, in the tutorials week. But for those who were not here, I'm just saying which one we used in our paper. So the main results that we already obtained are the duality, that we have both duality formulas for the both problems. We also have the characterization of the solutions, like what is the relation between minimizer of the primal and the maximizer of the dual. We also have nice results regarding the convergence, so that if you send, for example, tau1 and tau2 to infinity, that you actually recover this problem. So we not only recover the same value of the QOT, But we also recover that the minimizer converges to the minimizer, and the maximizers converge to some maximizers of the dual. And we also, for the balance problem, we define the special sinkhorn iterations. They are very implicit, so they're not really computable in a very easy sense, but we define it and we show that it's a sort of a maximizing sequence and it converges. So let's talk about the balance problem that we call. So here we don't have the unbalanced terms, so this is a constraint problem in the primal. So we need to here make sure that when we want to minimize, we want to make sure that we have correct marginals. And we know that the dual will have the following shape. So as Lorenzo mentioned already in the previous talk, so the typical assumptions that we have on the phi and psi is that that both of them are convex superlinear and bounded from below. And as Lorenzo mentioned, if phi is strictly convex, then psi is differentiable. So it's something that we also use in the proof. So sometimes we omit in the proof the dependence on phi because we directly work with the dual and we say, okay, let's look at the dual, and we just say, okay, let's psi be strictly convex and C1, and we can recover uniqueness of the maximizer up to translation. We can recover the shape of the what is the condition to be a maximizer. Okay, so this is the main result that we had in the paper. Here, for simplicity, we kind of considered that our rho and sigma are definite positive, so they do not have a kernel. This sort of helped us to find the bounds on the infinity norm of our maximizer. So this was just a trick, but in general, if you want to consider just any quantum density matrices, you would have to work on the orthogonal space of the kernel. So we showed that the duality holds for the balance problem. We showed that there is a unique up to translation pair that actually maximizes the dual problem. And we showed that there exists a minimizer of the primal. And if the function psi, which is in the dual, is C1, then we can get this nice formula for the minimizer of the primal, where U star and V star are the maximizers of the dual. And it doesn't really matter which maximizers are they, because U star plus V star doesn't depend on if you shift it right and left in U and V. So we have always this translation invariance, which is a little bit annoying in a sense if you want to get some coercivity. But in our proof, what we notice is that if you want to maximize the problem U and V in all semi-definite positive matrices, due to the shifting, it is exactly the same as if you also constrain that your first eigenvalue of the V is equal to 0. Because it doesn't matter if you reshift it in two directions. You can always fix one of the eigenvalues, and then you just will have just one pair. So what is nice about this is that with this assumption, we can easily show that we can obtain the bound on the eigenvalues of U and V that depend on. So what we have here, if U and V satisfy the assumption that V has the smallest eigenvalue, 0, and we have a bound for the dual function for some constant m, then we can find the constant that depends on this constant m, on rho sigma, and the dimension of the tensor product. So here, in the original paper that we wrote, we also have a dependence on epsilon, but in the new proof, we got rid of this dependence on epsilon. So especially if you make the assumption, because we want to send epsilon to 0, so as long as epsilon is more than 1, we can get rid of this dependence. And the dimension of h1 times h2, it actually pops up only from the fact that we have some lower bound on the function psi. So if the smallest value of the psi is 0, then we don't have dependence on the dimension of the space at all, which is pretty nice. Okay, so I hope I'm not moving too fast. Okay, so how can we attack the problem? Like, and how do we show the duality? So the general strategy is like we try to avoid Fenchler-Rockefeller theorem. We just want to show that first the primal problem is bigger than dual, and this is quite easy to show if you, for example, use the like Fenchler-Young inequality for matrices. I can write it on the board probably, that if you have gamma self-adjoint on some space H, and here H is finite dimensional, so it's sort of isomorphic to C to some power n, and W also self-adjoint. If H is finite dimensional, they're the same, so we can always say that the trace of phi gamma plus trace of psi W is always greater or equal than trace of W gamma. So this is like the Fenchler-Young inequality for the matrices. So here, phi and psi again are the Legendre transforms of each other. And what we try to do is like we multiply everything by epsilon here and divide by epsilon there. And we choose specifically W that is of a shape U plus V minus H. And then if gamma has the correct marginals, then we just get, like if we reorder things around, then we get that the primal is bigger than dual. And what else? Next, we try to show that the minimizer of the primal and the maximizer of the dual exist. This is a pretty straightforward proof using direct method of calculus of variations, especially if you, let's say, like for the dual, since we know this recentering, like we can bound U and V that satisfy this. So the maximizing sequence will be a bounded sequence, so we extract a convergent subsequence. So the maximizers exist. And we also established the so-called optimality condition for the transforms, which are like epsilon entropic transforms. By this I mean that my entropic transform U bar is the argmax of D in the variable U. So you fix a value V and you maximize in U. So this U is like the transform of V. So what is our optimality condition is that if, so here we have the assumption that psi is strictly convex in C1, and then these transforms are actually unique, so they're like, there is a unique argmax. The uniqueness of argmax only comes from like the fact that psi is strictly convex, and this must satisfy these special Euler-Lagrange equations. So this is actually very related to the classical sense. Like in the classical sense, especially if we do entropic regularization with the Shannon entropy, here we will have like the marginal rho is equal to the integral of the exponential of U plus V minus H over epsilon. And if we separate it, like because it's the integral only in one variable, we can explicitly recover the Sinkhorn algorithm. So this is precisely the condition for defining the Sinkhorn algorithm. And as you can see here, if these two conditions happen simultaneously, so if like we have some U bar and V bar that satisfy this, then this is exactly the condition for having the correct marginals. And at the same time, if we have U and V bar at the same time, then like U is the argmax of D and V is the argmax of T. So these are the maximizers. So this is like these are the essential conditions that the maximizers satisfy, and we heavily use it to show the duality.
Nataliia, and these the argmaxes are calculated in the theorem using the U and V from the proposition, the previous proposition, or?
So Sorry again?
Your UV that you're fixing here when you're calculating U bar and V bar here, are these UNV coming from the UNV you get from the previous proposition?
So if we don't have the, like, here we can actually use any UNV, but we can always recenter, like say that we take, if V doesn't satisfy that the lambda 1, like the smallest eigenvalue of V is 0, we just reshift it, and then like actually we don't really need the reshifting here. Yeah, here it doesn't, you don't need the reshifting. So, however, yeah, I think we may need the reshifting to show that this argmax in the one variable exists, because we want to make sure that like this the sequence that maximizes for the fixed U is converging. Yeah. Although if U is fixed, then probably it's there is no problem to
you want to converge, yes, but if you fix U, then the argmax exists. Any U, you can do it for every UNV.
Yeah, I think we don't need it here. I don't remember precisely the proof, but I'm pretty sure we don't need it. Okay, so here, as I mentioned, that if U bar and V bar are like this at the same time, that this happens, then gamma must have this shape. So this is the general idea. All right, so here we can define these so-called Synchrony type iterations. And by this, I mean that we want to define it through argmaxes, but it's not enough, because we want to show that this sequence will converge. And if we want to do it so that it converges, we first need to do the argmax, and then recenter it by some constant. And we choose a constant in such a way that the first eigenvalue of this reshifted one is 0. So even if after the iteration of argmax, if you just take an argmax, you may not obtain the one that has the 0 eigenvalue. If we reshift it, it will have the 0 eigenvalue. And since this is argmax, it's for sure increasing the sequence, the value of D. So we have this constant from below. So we can easily bound this Vn and Un. So if we get rid of this part, this is essentially, if we look at the classical case, these are the standard Synchrony iterations, because the argmax is given by this integral of like exponential. So here is, this condition is only to show that this sequence converge. All right, so what we show in this proposition, that this sequence is actually converging to a maximizer of D. And in fact, this sequence like converges strongly, so like we don't need to extract a subsequence. And moreover, the limit also has the the eigenvalue of V equal to 0. So, and at the same time, if we define at each step the gamma n, that it has this special shape, that it actually converges to a gamma star, which is the minimizer of the primal problem. So in this case, like we kind of define the special maximizing sequence, and it also converges to, like if you define gamma n, it converges to a minimizer of the primal. All right, so now I'm finished here talking about the balance problem. Let's talk a little bit about the unbalance that was never mentioned yet before. So here, as I said somewhere in the beginning, we introduced these soft constraints on the marginals. So instead of forcing that the partial traces are equal to rho and sigma, we add the relative entropy. And here we define it in an interesting way, because like this definition will also work for all semi-definite positive matrices, not only with trace 1. So you might have seen the definition of relative entropy without these terms, but it's because they have like trace equal to 1. So if we include this, then we can formulate the primal functional for not only density matrices. Especially, this is sort of like the correspondence to the classical case. In the classical case, there is also like a well-known like unbalanced classical optimal transport, but instead of where your marginals may be pictures, so they're not normalized to 1, and you just have some positive measures instead of probability measures. So here we try to kind of replicate it, so we don't need that rho and sigma are density matrices. We can just say, okay, they're just positive, and we want to formulate this problem like identically to the classical case. So the interesting part happens in the dual, because in the dual, we get this part that like is epsilon, or this exponential of something plus log of rho. So this is very different from, let's say, dual functional in the classical unbalanced, because like we can separate the exponential of something plus log of rho. It will be just exponential times rho. So here we don't have it, but yeah, this is the actual dual formula that arises from considering this, if you, again, use this similar trick like with differential Young inequality. So what is the advantage of this? So here now, the primal problem is also unconstrained, because we don't have the strict planarization of the marginals. We also do not have the invariance translation for the dual. So before we had the dual of u and v is equal to dual of u plus lambda and v minus lambda. We don't have it anymore. So if actually, because of these exponentials, this is a strictly convex function, so the maximizer of the dual is unique. So we don't need to do anything. At the same time, with this choice of entropy, like the omega k entropy that we used, this is well defined only for definite positive rho and sigma, and also it's kind of badly extendable for the infinite dimensional case, because like we have this log of rho, which we cannot really avoid, and we cannot like put it downstairs like by saying that epsilon of rho, like exponential of something times rho, because it's not the actual dual that comes from the differential Young. All right, so both problems are now strictly convex and concave. So this is convex, this is strictly concave because of the entropy. And a final remark, which is kind of interesting, that for all tau and for all u and v, this dual problem with the unbalanced terms is always smaller than the dual without the unbalanced. This actually comes from the Klein's inequality, but like it actually shows that if you want to optimize this problem, you get the lower bound to the one that you had before. All right, so here is another big theorem that we had. So if rho and sigma are definite positive, again, for simplicity, we show that the duality holds. So we show that the inf is equal to the sup. There exists a unique pair of u and v that maximizes the dual functional, and there exists a unique minimizer, so that if psi is differentiable, then we have this actually the same formula as we had in the previous one that was balanced, which is here is kind of interesting, because like we have a different problem. We don't have like these marginal constraints anymore. We have the soft one, but the shape of the minimizer is exactly the same. So here I can talk a little bit about the optimality condition of the maximizers for the unbalanced problem. So here, if you want to look at the argmax of d epsilon tau, then they must satisfy this Weirder Euler-Lagrange equations. So both formulas are coming from just, you take a Fréchet derivative in some direction, and you just get that this must be equal to that, because if you want a Fréchet derivative to be 0. So this is interesting just like the pretty interesting result in terms of the shape. So let's say if psi was an exponential again, then we'll have an exponential here as well. And here we have like this u tau and here u tau. We might try to think of solving something more explicitly if we could, but it's still some work in progress. So the other thing that we have is the gamma convergence results as tau1 and tau2 go to infinity. So here we are trying to show that if we send the unbalanced generalization to infinity, we recover the problem with correct marginals. So we do show that the gamma, okay, here is a typo. We show that f of epsilon that f epsilon tau gamma converges to f epsilon, and the minus d u tau converges to minus d epsilon tau. So here I lost the minus, but it's like the idea is this is like usual. We show that the something gamma converges. We show some equicoercivity conditions on the maximizing sequences, and then we show that, okay, then from this, we can use the bazooka of gamma convergence, that we have that the optimizers are also converging. So we show that the optimizers do converge. And here is another thing that we also showed, is that if we take this epsilon and tau transforms, which are like the bar that are argmax of d epsilon tau in one variable, we can show that actually this tau epsilon transform converge to the epsilon transform as well, as tau goes to infinity. And it actually doesn't, like, you don't need to fix one variable, you can just take a sequence here as well. So you just, if you have some v tau converging to v, then the argmax with v tau will converge to the argmax of v with when tau goes to infinity. So this is probably, okay, there is the last slide that we were postponing until the very end of the paper. So we actually showed the duality also for non-smooth psi. So before, we only considered that the regularization has to be like C1, has to be strictly convex. In fact, you can show that the inf is equal to sup also without these conditions, as long as phi and psi are convex. I mean, you just take phi are convex, so psi is the Legendre transform, so it's also convex. So the only thing that we ask is that the rho and sigma are actually definitely positive. So what we so with these two conditions, we recovered the duality for both problems. And the main idea for showing that is to use the modification trick. So we modify with some kernel that is strictly convex and differentiable. And then we just show that the modified problem is the one that we had before. And we take a limit with the modification kernel, and we recover these two. So it's a pretty straightforward also trick from calculus operations. So I decided to skip it here because it's pretty technical. But the duality holds and is nice. So here, the hardest part is like to show that this sup is a max. Like, what are the conditions that we need on psi? Because like we know that max for sure exists if psi is like if is good in terms of like it's strictly convex or differentiable. And also, we just want to know what are the good regularizations for like showing the computationals, in general for the computations. All right, so here how much time? I have a lot of time. Yeah, I'm sorry for going too fast. So here is since I have a chance, I would like to advertise an event that I'm organizing also with Augusto this summer. So it's a summer school that we do in Lviv in Ukraine. So it's a summer school on optimal transport, and it's already confirmed. So it's going to happen for sure, and we're just like looking for students to go for our school. So the deadline for the application is in 2 weeks. You don't really need anything for the deadline, but if you are if you're a student or if you're a professor and you have students who would like to go, you can encourage them to apply. We don't really need a lot for the application, no recommendation letters, just maybe transcript of records, and that's it. And from the list of the speakers, so there will be me, there will be Augusto, there will be Lorenzo, and 2 more people. So this is the final thing that I wanted to mention, and thank you very much.